Welcome to Math with Professor V. In this video, I'm going to work through a bunch of exercises where we have to find the equation of a line or plane in three-dimensional space given certain pieces of information. And this is all in order of increasing difficulty. So at the end, I'm going to do some spicy stuff like distance between two skew lines, distance between parallel planes, and other very interesting things. Now, if you haven't watched the introductory video lecture on equations of lines and planes in three space, I'll link it in the description because I'm just gonna work through the homework exercises in this video and not give a lecture laying any of the foundation down. So make sure you have the basics under control. And on that note, let's just jump right in. So first problem says, find a vector equation and parametric equations for the line. And it tells us the line goes through the point -1, 8, 7, and it's parallel to the vector 1/2, 1/3, 1/4. So this is my direction vector V, and the components that are given are A, B, and C. And remember, when we have the vector equation for a line in space, we write it as ABC times T plus X naught, Y naught, Z naught, which is right here. That's my point P naught. X naught, Y naught, Z naught. So I can put this all together and we have R of T equals 1/2, 1/3, 1/4 times T plus -1, 8, 7. Okay, that's the vector equation. But more commonly, we work with the parametric equations of a line. So from here to get the parametric equations, we're going to have one for x, one for y, and one for z. And we set the corresponding components all equal to each other in order to come up with the parametric equations. So the x component would equal 1/2 times t plus -1. So I'm going to write x equals 1/2 t minus 1. Y would equal 1/3 times t plus 8. And then z is going to be 1/4 times t plus 7. And those are my parametric equations. That's it. This one was straightforward. Just want to make sure we all are under control. We're good? Okay, moving on. Find the equation of the line that goes through the point 5, 7, 1, and it's perpendicular to the plane 3x minus 2y plus 2z equals 8. So remember, when we're given the equation of a plane, we should be able to identify the normal vector to the plane by looking at the coefficients of x, y, and z. So a vector that is normal to the plane is one of the key identifying factors that we need when we write the equation of a plane. And I can see right here, this plane's normal vector has components 3, -2, and 2. Okay, now they told me the line whose equation I want goes through this point here. That's great. So that's my x naught, y naught, z naught. And our line is perpendicular to this plane. So our line, I don't know where it's floating, somewhere over here, it's perpendicular to the plane as well, which means it's parallel to the normal vector. So I can use the normal vector as the direction vector for our line. I'll summarize that. Our line is parallel to n. So we can use n as our direction vector. Does that make sense? Okay, good. So I'll again write out the vector equation. R of t equals n, in this case, so 3, -2, 2 times t plus 5, 7, 1, the point that the line goes through. That's the vector equation. Then the parametric equations, we're going to have one for x, one for y, one for z. We'll have 3t plus 5 for x. Take 3 times t plus 5. Then we'll have negative 2t plus 7 for y. And lastly, 2t plus 1 for z. Good? Okay, beautiful. Hopefully so far things aren't too wild. We're gonna build. Next exercise, find parametric equations and symmetric equations. Okay, I'll explain what that is if you need a refresher. For the line, and this is the line that goes through the points 12, 9, negative 13, and negative 7, 9, 11. So what do I need to write the equation of a line in 3 space? I need a direction vector and I need a point. Well, I have 2 points. So with those 2 points, I can find a direction vector, and then I can just pick one of them to be P naught. So let's go ahead and make our direction vector. I'll call this P naught, and then this can be P. So my direction vector V goes from P naught to P, and it would have components negative 7 minus 12, so that's negative 19, 9 minus 9, which is 0, and then 11 minus negative 13, so 24. Now, alternatively, you could have gone from P to P naught or called them whatever your little heart desired. It doesn't matter. So if instead you had 19, 0, negative 24, that's totally fine as well. So there's some options here, and it's not like this direction vector looks so much better than this one over here. So I wouldn't say one is preferred necessarily in this case, okay? Just for the sake of having the first component positive, let's use this one though. All right, and then let's write the parametric equations. And again, you can use whichever point you want for x naught, y naught, z naught. I'm just going to use the first one that was given, but alternatively, you could use negative 7, 9, and 11. It doesn't matter. So I'm going to have x equals 19t plus 12, y equals 0t plus 9, so just 9, and then z equals negative 24t minus 13. So that's one option, okay? Now, to find the symmetric equations, this is where we solve for t, and then we don't actually write the parameter out in any of the equations. We just set the parameters values equal to each other. So what the heck am I talking about? Well, if you look at this first equation, if I solve for t, I'd have x minus 12 over 19 equals t, yes? And then I can do the same thing over here, z plus 13 over negative 24 equals t. So my symmetric equations come from just setting these two quantities equal to each other since they both equal t, right? So we can just write x minus 12 over 19 equals z plus 13 over negative 24. Now notice I didn't deal with y equals 9 because there is no parameter t here. So I couldn't solve for t, it's impossible. And that's because the y component in my direction vector is 0. 0 times t, that's why the t is missing here. So anytime that happens, then you're not going to have equals that other variable. You just put a little comma, and then you write out this equation here that you're basically stuck with, which tells us though that y is always equal to 9. And that shouldn't be a surprise because look at these points here, P naught and P. See how the y coordinate is 9 on both of them? So y is not changing. That's why the y component for the direction vector was 0. Y is constant on this line. Okay, how was that? So let's box this. This is our answer. These are the symmetric equations. Okay, very good. Now let's look at another similar sort of problem, which is going to have a lot of use to us later in the semester. Find a vector equation for the line segment from 6, negative 1, 9 to 7, 6, 0. So we want it to start at 6, negative 1, 9 and end at 7, 6, 0, not extend forever. So the way we're going to do it is by restricting our parameter t. I'll tell you how at the end. First, let's just come up with the parametric equations for the line that connects those 2 points the line that extends forever, and then I'll show you how to restrict the parameter, okay? I need a direction vector for the line. So I'm going to do that by connecting these 2 points. Let me call them P and Q. So PQ would have components 7 minus 6 is 1, 6 minus -1, that's 7, and then 0 minus 9, -9. Okay, so I can use that as my direction vector for my line, and then pick your favorite point to use for x naught, y naught, z naught. I'll just use this one. Actually, since we're starting there, I do have to use it. Excuse me. You have to use that as x naught, y naught, z naught, since the segment starts there. So here's my parametric equations. X equals 1 times t plus 6, y equals 7t minus 1, and z equals -9t plus 9. And then all you need to do is restrict your parameter t to go from only 0 to 1. And you might say, what in the world? Well, notice something. If t is 0, x is going to be 6, y is going to be -1, and z is 9. So that's the point P. And then when t is 1, come and plug it in here. Plug in 1 for t here. Tell me, what's the ordered triple that we get? If t is 1, we get back 7, 6, 0. That's Q. So then we have just the line segment from P to Q. As long as we use that initial point as x naught, y naught, z naught. So you have to use that first point when you write your parametric equations. And then because we used these 2 points, P and Q, to make the direction vector, when I cut off t at 1, it's going to take me all the way to that second point Q. And that's how we get that line segment. So I don't usually check that t equals 0 gives me the first point, t equals 1 gives me the second point, because I'm pretty comfortable with this process, but feel free to just double check as much as you need. And then later in the semester, you will need to come up with parametric representations for line segments, and this is exactly how you do it. So save this for later, okay? Pretty much everything you're going to save for later, but this skill in particular is important. Okay? How are we doing? Shall we move on? Okay, good. Next, determine whether the lines L1 and L2 are parallel, skew, or intersecting. If they intersect, find the point of intersection. So here I have the parametric equations for 2 different lines. And in order to figure out if they're parallel, skew, or intersecting, I need to look at the direction vector for each of the lines. So can you tell me what the direction vector is for the first line? Just look at the coefficients of t from the parametric equations. The direction vector has components 2, -1, and 3. Okay, good. And then what are the components for the direction vector for the second line? Again, look at the coefficients of s this time for -2 and 5. Okay, beautiful. Well, in order for L1 and L2 to be parallel, their direction vectors V1 and V2 would need to be parallel. How do we check if they're parallel? Well, we would need to check our V1 and V2 scalar multiples of one another. So is V1 equal to some constant times V2, where C is a scalar? Well, no, I can already tell not happening. This component is half of this component. Ooh, then maybe you're excited. This one looks like half of this. Oh, but this should have been 5 halves for them to have been scalar multiples. So no. So the lines are not parallel. Now I want to check, okay, well, do they intersect? Do they intersect? Well, what does it mean for 2 lines to intersect? It would mean that they share a point in common. So here's line 1, here's line 2. If they intersect, then they have in common some ordered triple, x, y, z. which means that the x components, y components, and z components should all coincide at some value. So that would mean 3 plus 2t from line 1, the x coordinate would have to equal 1 plus 4s on line 2. And then 4 minus t from line 1, the y component, the y coordinate, would have to equal 3 minus 2s on line 2. And then 1 plus 3t, now I'm setting the z coordinates equal to each other, equals 4 plus 5s. Okay, now notice here, this is a little interesting. We have 3 equations, but we only have 2 unknowns. So what do? In this case, I'm just going to work with 2 equations at a time, solve that system, and then check if my solution works in the third. So let me just work with equations 1 and 2, all right? Let me use the elimination method. So I'm going to multiply equation 2 by 2 and then leave equation 1 alone. So 3 plus 2t equals 1 plus 4s. And now I'm going to double the second equation. And then I'll have 8 minus 2t equals 6 minus 4s. And then if I add these together, all my variables cancel out and I just am left with 11 equals 7. Well, already things are off to a horrendous start. 11 certainly doesn't equal 7. So there's no solution to this system of equations. I don't even need to carry on any further. All right, so if there's no solution, then that means the lines do not intersect. In fact, we can be more dramatic. The lines never intersect. So if the lines are not parallel and they don't intersect, then that implies they are skew. Ooh, okay. Very good. Let's try a couple more like this, okay? See if you get the hang of it. Here we have symmetric equations. Line 1 equals x minus 2 over 1, which equals y minus 3 over negative 2, which equals z minus 1 over negative 3. And then we have line 2 symmetric equations. Okay, let's write down the direction vector for each of the lines. So direction vector for line 1 has components. Remember, now a, b, and c are in the denominators. So it would be 1, negative 2, negative 3. And then the direction vector for line 2 has components 1, 3, negative 7. Well, if I'm checking for the lines to be parallel, remember the direction vectors need to be scalar multiples of one another. And I can certainly tell they're not scalar multiples. So these vectors are not parallel. So L1 and L2 are not parallel. Now I want to check, do the lines intersect? And I need to set up a similar system of equations that I did before. But you know, it's not easy to do with these symmetric equations. So I'm going to say let's switch and write with parametric equations instead. It's going to be better. So remember, each of these little quantities from the symmetric equations is equal to t. So let's go back to the parametric equations. T equals x minus 2 over 1. Also, t equals y minus 3 over negative 2. And t equals z minus 1 over negative 3. And then I can solve for x, y, and z now, so I get back my parametric equations. So x equals t plus 2. Then we'll have here y equals negative 2t plus 3. And z equals negative 3t plus 1. Now let's move on to line 2. And this time, let's use a different parameter so we don't get everything confused. So I'm going to use s. S equals all of these. So here we'll have s equals x minus 3 over 1. I don't need to write that. 3s, let me not skip steps. I got too excited. S equals y plus 4 over 3. and then s equals z minus 2 over negative 7. So then again, let's solve for x, y, and z, get our parametric equation. So x equals s plus 3, y equals 3s minus 4, and then z equals negative 7s plus 2. Everything good? Okay, so we can set up our system of equations just like the last problem. Equation 1, I'll set the x coordinates equal to each other. So t plus 2 equals s plus 3. Setting y's equal to each other, negative 2t plus 3 equals 3s minus 4. And third equation, negative 3t plus 1 equals negative 7s plus 2. So same thing, just work with two equations at a time, solve for t and s. I'll just work with 1 and 2, and let's try substitution. So let me get t by itself in the first equation. T equals s plus 1. And then now I'm going to plug that in for t into the second equation. So negative 2 times s plus 1 plus 3 equals 3s minus 4. So negative 2s minus 2 plus 3 equals 3s minus 4. 1 equals 5s minus 4. So 5s is 5. Cool. So s is 1. And then if s is, whoa, what is that weird shape? So if s is 1, let's see, didn't I have up above? Yeah, t equals s plus 1. So then that means t would be 2. And this solution came from working with equations 1 and 2. So now I need to see, do they satisfy my third equation? So let's check now in 3. Is negative 3 times t is 2 plus 1. Put a little question mark. We don't know, right? Don't just put equals. Then you're lying. Does it equal negative 7 times 1 plus 2? So negative 3 times 2, that's negative 6 plus 1, negative 5. Does that equal negative 7 plus 2, negative 5? Yes, it does. Yay! Okay, so yes, that means they intersect. And then we need to find the point of intersection. So you have two options. You can either take s equals 1 and plug it into the second equation, or t equals 2 and plug it into the first. You'll get the same thing. So they intersect at, I'm just going to plug in 1 for t into line 1. So they intersect at, if t is 2, I'd get 4 for x, negative 4 plus 3, negative 1 for y, and then negative 6 plus 1, negative 5 for z. And voila. Oh, very good. Very good. Hopefully that was satisfying. Okay, next one. Find an equation of the plane. Ooh, okay. So we need the plane that goes through the point 5, negative 2, 4, and it's perpendicular to the vector negative 1, 2, 3. Well, really, they just set us up for success because remember, when you write the equation of a plane, you need two things. You need a point on the plane and a vector normal to the plane. That's it. That's how you get a positive ID on a plane. You need some point on the plane to nail it down, and then you need a vector normal to the plane in order to identify its direction. So we're good. For my normal vector, I can use what was given, negative 1, 2, 3. Since this vector is perpendicular to the plane, same thing, it's normal to the plane. And then here's my point, x naught, y naught, z naught. And remember, the dot product of all x minus x naught, y minus y naught, z minus z naught, all x, y, z on the plane with this normal vector should be 0. So that's how we form the equation of a plane. So I'm going to take negative 1 times x minus x naught plus 2 times y minus y naught is going to be plus 2. And then plus 3 times z minus 4, this equals 0. And then just clean it up. You want it in standard form. So all the variables on the left, constants on the right. So we have negative x plus 2y plus 3z equals, this is 5 plus 4 is 9. Minus 12 is negative 3. And then if I move it over, it's 3. And sometimes, actually, they'll leave the answer like this in the back of the book. It irks me because usually we say that standard form x's coefficient should be positive. So I'm going to switch it. Just check with your instructor if they care or not. X minus 2y minus 3z equals negative 3. I would say don't leave your final answer with the negative in the front, but it's not like it's never done, okay? I just think it's ugly. And that's it. Okay, that was a warm-up. Let's be real. Next example. Find the equation of the plane that goes through the points 2, 1, 2, 3, negative 8, 6, and negative 2, negative 3, 1. So let's think about what we're given in this problem versus the last one. Remember, we need a point. We have that. We have plenty of those. And then we need a vector normal to the plane. So they just gave me 3 points that were in the plane. Let me call them A, B, and C. They're just floating around, okay? How can I get a vector normal to the plane? Well, I'm going to make a vector connecting A and B. I'm going to make another vector connecting A and C. Then if I take the cross product AB with AC, I know that vector is mutually orthogonal to both those vectors. And then I will get a vector normal to the plane. Okay, and that's a pretty standard process. So just be careful. If you make a little careless mistake with your arithmetic, it derails everything. I know, so we just have to be oh so careful. So AB would have components 1, negative 9, 4. AC has components negative 4, negative 4, negative 1. And then now I need to find their cross product. And I'm not going to write out a whole 3 by 3 and do the determinant. I just do it in my head. So I showed my class. I don't even write I hat, J hat, K hat. I just kind of imagine they're there. And I'm imagining all this is happening. So then this is 9 plus 16 for the first component. Then the next one, I multiply the opposite diagonal order since there's a minus sign. So then that would be negative 16 plus 1 exactly. And then lastly, we're going to have negative 4 minus 36. If you need to review cross products, I'll link the video in the description. Okay, so this ends up giving us 25, negative 15, negative 40. And I'm looking, everything's divisible by 5. And if I divide a vector by a scalar, I'll get a new vector that's parallel, right, to the original one. Well, any vector parallel to this normal vector, say it's scaled down, is still going to be normal to the plane. It'll just be nicer to work with when we write the equation of the plane. So instead, if we want, we can use 5, negative 3, negative 8. If you don't do this, you're just going to have to simplify at the end. So I'd rather get it over with now and deal with smaller numbers from the get-go. And then from the points that were given, just pick your favorite. I like you, 2, 1, 2. Let's go. So 5 times x minus 2 minus 3 times y minus 1 minus 8 times z minus 2 equals 0. You could have picked any other point as well, B or C, and you'll actually get the same exact equation. So the equation of a plane is unique. The equation of a line is not. Like equations of planes, once they're fully reduced and simplified, if we have the same standards, they're unique. Equations of lines are not. Okay, this anyways ends up simplifying to 5x minus 3y minus 8z equals, this is negative 10 plus 3, so that's negative 7 plus 16. Negative 7 plus 16 is 9. So then if I move it over, it should be negative 9. Is that not correct? Sounds good. Let me double check. Yes, all is well. Okay. Here we go now. Things are going to get more spicy. We need the equation of the plane that passes through the point 3, 5, negative 1 and it contains the line x equals 4 minus t, y equals 2t minus 1, and z equals negative 3t. Okay, so I'm going to draw a little picture for you, and I recommend you do the same. You don't have to, but it just helps me kind of imagine what I'm given and what I need. So the plane passes through the point 3, 5, negative 1, and then it contains this line here. Okay, somewhere in the plane, I don't know. There's the line. So just always think back to what do I need to write the equation of a plane, and what have I been given? I need a vector normal to the plane, and I need a point. Well, I already got the point. How can I get a vector normal to the plane? Think back to what you've already done successfully in previous problems. Then you don't feel like you have to invent new math. You know what I mean? Like, that's not what's happening here. Oh, look at this last example. We had two vectors that were in our plane, and we took their cross product and got the normal to the plane. Can we somehow do something similar now? Can I somehow find two vectors that are in this plane? Yes. I'll tell you one vector that's in the plane, the direction vector of the line. Can you tell me what the direction vector is from the line? The direction vector has components -1, 2, -3. So the direction vector of the line, somewhere over here, I'll call that V. Great. Now I need one more vector in this plane, and then I can cross it with V and end up with a vector that's normal to both of those vectors and therefore normal to the plane. So what we need to do is connect this point to any old point that's on the line. I think the easiest point to extract is just substituting in 0 for t. So let me get another point, we'll call this P, and my point Q from plugging in t equals 0 is on the line, and it has coordinates 4, -1, 0. Q is on the line and therefore on the plane. So let me connect P to Q, doesn't really matter which way, or Q to P. So if I do P to Q, then I'm going to have component 4 minus 3, so 1, -1 minus 5, -6, and then 0 minus -1, so +1. So PQ is a vector in the plane also. Okay, so here's P. I don't know where Q is on the line. It's somewhere, and I just connected them. Boom. Okay, so I'm going to take the cross product now. If I take V and cross it with PQ, the resulting vector is normal to both. Remember, cross product, result of a cross product is mutually orthogonal to the original two vectors, and therefore normal to our plane. Okay, great. So V has components -1, 2, -3. PQ has components 1, -6, 1. And then their cross product gives me the normal, which has components -16, -2, and 4. Now, you can use that, but I recommend let's scale everything down, divide by -2. So instead we can use 8, 1, -2. Okay, beautiful. And then pick your favorite point. You could use Q or P to write the equation of the plane. Let's just work with P. But if you want to try Q on your own, you should get the same thing as me. So we'll have 8 times x minus 3 plus 1 times y minus 5 minus 2 times z plus 1 equals 0. So then we're left with 8x plus y minus 2z equals, this is -24 minus 5, -29, minus 2, negative 31, and then move it over to the other side, positive 31. Bravo. How you doing? So I'm pretty sure I did examples all like these in the video lecture, but different, different values and whatnot. All right, next exercise, find the equation of the plane that passes through the point 314, and it contains the line of intersection of the planes x plus 2y plus 3z equals 1 and 2x minus y plus z equals negative 3. So this is very similar to the one that we just did. We're given a point on the plane, and we're given a line that is on our plane. However, unlike the last problem, we don't know what the direction vector is currently for that line of intersection. So let me kind of draw what's going on. We have two planes that are intersecting, and most of the time when two planes intersect, they do so at infinitely many points where there's a line at their intersection. Okay, so maybe let me adjust this one a little bit, and we can draw approximately, maybe their line of intersection looks something like this. Okay, there's their line of intersection. So I'm trying to find the equation of a different plane, a new plane that contains this line of intersection and one other point that was given to me. Let's just call this point P, 314. So point P is somewhere over here, 314. And we're trying to find the equation of a different plane. It's floating out here somewhere. And then hopefully you can see I'm trying to make it look like this point P is in this plane as well as this line of intersection. Here's the plane whose equation we're trying to find. Okay, so like I said, think back to the last problem. We were given a line in the plane and a point. We used the direction vector of that line because we said, okay, well, the direction vector of that line is also a vector in the plane. And then we connected the point to the line that we were given. I'm talking about the last problem. Made another vector in the plane, crossed both of those, and then got a vector that was normal to our plane. So we're gonna basically do the exact same thing. It's just first I have to figure out what is the direction vector of this line. So here's what you need to do. This line of intersection here, right? It is perpendicular to both of the planes that were given to us here. This line of intersection lies in the first plane, therefore it is perpendicular to the normal vector of that plane, and also this line of intersection lies in the second plane, therefore it's also perpendicular to the normal vector of that plane. So to get the direction vector of the line, let's just call it V. To get the direction vector V of the line of intersection, I'm going to take N1 and N2. Those are the normal vectors from each of the planes, the given planes, and cross them. You don't have to write out all of this process, but I think it's helpful when you're first trying to get the hang of it, and then you can look back at your work and make sense of it, because sometimes you'll just see you crossed two vectors and not understand the reasoning behind doing so. So normal vector number 1 from the first plane has components 1, 2, 3. And then normal vector number 2 has components 2, negative 1, 1. That's from the second plane, okay? So now we're going to cross them, and we will get the direction vector of this line. And I'm just going to do it quickly in my head. So this is 2 minus negative 3, which gives us 5. And then we have 6 minus 1, so that's 5. And then negative 1 minus 4, negative 5. Okay, so this is the direction vector of our line. You know, we can scale it down and just use 1, 1, negative 1. This is the direction vector for our line, and this vector is in our plane. So this vector is in our plane. Hooray. I just need one more vector in our plane. So here's the direction vector, V. It's in our plane. Now what I need to do is find some other point on this line, and I can connect it to the other given point in our plane, make a second vector in the plane, and then I'll cross those two vectors and bam, I got the normal to my plane. So how can I find another point that's on this line? There's infinitely many points on this line of intersection. You just have to say, all right, what's going to satisfy both of the equations here for these two planes? And you kind of just have to play around with it. Sometimes it's very obvious that maybe 0, 0, 0, 1, 0, 0 is on both planes. Looking at it right now, nothing is like screaming at me that is very clearly on both planes. So we're just going to play around with the two equations right now. So I need a point on the line of intersection. Okay, so here's these two planes, x plus 2y plus 3z equals 1, and then 2x minus y plus z equals -3. Sometimes I like to start off just letting one of the variables be 0. And this will work just as long as the line of intersection does cross through whatever plane results. So let's just try letting z equal 0 and see if that's going to get us anywhere. So if I let z equal 0, then I have x plus 2y equals 1, 2x minus y equals -3. I want to solve by elimination, so let me double this equation. So 2x, or actually let me double the other one. I'll leave that one alone. X plus 2y equals 1, and let's multiply this one by 2, so then now it's 4x minus 2y equals -6. Then if I add them up, I get 5x is -5, so x is -1, and then if I substitute in -1 for x back here, add it over, I get 2y equals 2, so y equals 1. So I got x is -1, y is 1, and this was assuming z is 0. Now this won't work if the line of intersection doesn't go through where z is 0, the xy plane. So if you're not able to get a solution here, then just switch out. Instead of letting z be 0, let y be 0, or try letting x be 0. Sometimes you have to play around with it. Other times it's very obvious. There's like a nice point that they have in common. But anyways, hooray! This is another point on the plane. Let's call it Q. Not only is it on our desired plane, it's on this line of intersection. So say Q is over here somewhere. And then now what I want to do is make another vector that's in our plane. So I'm going to connect Q with P. Okay, so let's go ahead and do that. Q to P is in our plane. So Q to P would have components. Let me remind you what P's coordinates were. P was at 3, 1, 4. So Q to P would be -4, 0, -4. That is a vector in our plane. You know what? Let's just scale it down. We can use instead 1, 0, 1. That'll be easier. So now I have two vectors that are in our plane. Do you remember what they are? This one that we just got, 1, 0, 1. And also the direction vector for the line of intersection. So now the normal vector to our plane is going to be the cross product of those two. So 1, 1, -1 crossed with 1, 0, 1. These are both in our plane. So the normal vector to our plane would have components. Let's see. That's going to be 1, -1, -1, -2, and -1. So that is normal to our plane. Yay! So So then all I need to do now is put it together with either point P or Q to write the equation of the plane. You choose your favorite. Let me go ahead. I'll just use P. I need a little more space if you'll allow it. I got too excited. So then we have also point P with coordinates 3, 1, 4. So I can say 1 times x minus 3 minus 2 times y minus 1 minus 1 times z minus 4 is 0. And then x minus 2y minus z equals, this is negative 3 plus 2, so I'm at negative 1, plus 4 is positive 3, and then move it over, that's negative 3. Fabulous. So let me give you a little recap what we did, okay? That's the equation of the plane. We were told that our plane contains the line of intersection for two other planes and some additional point. So just like in the last problem, if we know our plane contains a line, that means our plane contains the direction vector of that line. And then if I can have one other vector in our plane, once I have two vectors that are in our plane, I can take their cross product, and that vector is the normal vector to our plane that we can use to write the equation. So first we had to find the direction vector for the line of intersection. I know the line of intersection lies in both of the planes that were given, so it's mutually orthogonal to both of their normal vectors. So we took the cross product of the normal vector, for each of the given planes. Bam, there's the direction vector for our line. Let's use a scalar multiple that's nicer to work with. Then we need to squeeze out one more point that's on this line of intersection. I decided to let z equal 0. Maybe try something else because there's infinitely many points on that line of intersection. You don't need to necessarily do exactly what I do. However, from here, once you have a point on the line of intersection, you're going to connect it to the other point that was given to us on the plane. We have now a second vector in our plane. I take the direction vector, cross it with this second vector, and at long last, here's the normal vector to our plane. Take that normal vector with your favorite point, either P or Q, and at long last, you arrive at the equation of the plane. Practice explaining this to somebody else. Okay? Good. Let's move on. I think that's one of the trickiest ones here. Now we need the equation of the plane that passes through the point 1, 5, 1, and it's perpendicular to the planes 2x plus y minus 2z equals 2 and x plus 3z equals 4. So our plane is perpendicular to the given planes with normal vectors. I'll say n1 has components 2, 1, negative 2, and n2, which has components 1, 0, 3. Well, that means the normal vector for our plane is also perpendicular to n1 and n2. So the normal vector to our plane is mutually orthogonal to both the normal vectors that were given for these planes. So if I just take their cross product, then I will have a vector normal to our plane. So let's find n1, cross it with n2. And let's see, that's just going to be, I'm imagining this is gone, that's 3. Next component's going to be negative 8 and negative 1. This vector is normal to our plane. Beautiful. Then they also already gave me a point that's in our plane. So we're ready to put it all together. 3 times x minus 1 minus 8 times y minus 5 minus 1 times z minus 1 is 0. And then just simplify now. So 3x minus 8y minus z equals negative 3 plus 40 plus 1 is 38, and then I'm moving it over to the other side, so now it's negative 38. That felt dramatically easier than the last one, I know. This is the order that they're in the textbook. I'm numbering them generically because I hate when they keep coming out with new additions and only a few things are rearranged and I have to like redo everything. So this is just generic numbering, but this is the homework I assigned my class. Okay. Moving on, determine whether the planes are parallel, perpendicular, or neither. If neither, find the angle between them. Use degrees and round to 1 decimal place. So in order to find the angle between the planes and determine whether they're parallel, perpendicular, or neither, I need to look at the normal vectors to each of the planes. So let's extract that first. Here's a plane. Its normal vector is 1, 4, negative 3. And then normal vector for plane number 2 is negative 3, 6, 7. Well, I can already tell n1 and n2 are not scalar multiples. So they're not parallel. The normal vectors aren't parallel. That means the planes are not parallel. Okay, that's done. What about perpendicular? How could I determine if the planes are perpendicular? If their normal vectors are perpendicular. How do we check that? Check what their dot product is. So 1 times negative 3 plus 6 times 4 minus 21. Ooh, that's 0. Perfect. So that means the planes are perpendicular since their normal vectors are perpendicular. Done. Good? Okay, let's look at another one. Again, let's figure out what the normal vectors are for each of these planes. N1 has components 1, 2, negative 1. N2 has components 2, negative 2, 1. Just by looking, I can tell these are not parallel. They're not scalar multiples of each other. Now let's look at their dot product. So N1 dotted with N2 would give me 2 minus 4 minus 2, right? No, minus 1, excuse me. Getting too excited over here. 2 minus 4 minus 1. So that's negative 3, which is not 0. So these planes are not perpendicular. Okay, so then it's neither. And if neither, they want the angle between the planes. So then we're going to go ahead to find the angle. We use the fact that we know cosine theta equals dot product of those normal vectors divided by magnitude of each. This is probably one of the most useful formulas you're going to have all semester. So N1 dotted with N2 is negative 3 over square root. So magnitude of N1 would be square root of 1 plus 4 plus 1, so square root of 6. And then magnitude of N2 is square root of 4 plus 4 plus 1, so square root of 9, which is 3. So then I end up with negative 1 over rad 6. So theta is cosine inverse of negative 1 over rad 6. And if we're rounding to 1 decimal place, as the direction said, then we'll say it's approximately 114.1 degrees. Okay. Sometimes directions will say give the acute angle, and all you would have to do in that case is you just take absolute value of this dot product. When that dot product is negative, that means cosine theta is negative, then it's between 90 and 180. We're in quadrant 2. But if you want an acute angle between two lines or planes or whatnot, then just make that positive, then you force it to be an acute angle between 0 and 90. Okay, one last one like this. Hopefully you're enjoying these. They're very straightforward. 2x minus 3y equals z. 4x equals 3 plus 6y plus 2z. So again, we're trying to figure out if the planes are parallel, perpendicular, or neither. They're not in standard form, so I can't tell what their normal vectors are just by looking at them when they're a hot mess like this. So let's rewrite them in standard form. 2x minus 3y minus z is 0. And then 4x minus 6y minus 2z is 3. So normal vector for the first plane has components 2, -3, -1. And then normal vector for the second plane has components 4, -6, -2. Ooh, they are scalar multiples. Notice 2 times n1 is equal to n2. So the normal vectors are parallel. Therefore, the planes are parallel. Okay, and then we're done. Hooray, that was the shortest one. How are you guys doing? I have a few more. Here we go. This is kind of building off what we did in a problem earlier. So 15, part A says, find parametric equations for the line of intersection of the planes. And then find the angle in degrees rounded to one place between the planes. So that part's straightforward, just like what we did earlier. Finding the parametric equations for the line of intersection, remember we need a point on the line of intersection, and then we will come up with how to find the direction vector for the line. Do you remember how we did it? The direction vector for the line, we find it by taking the cross product of the normal vectors to each of the planes. We'll talk about that in a minute, but first let's get a point on that line of intersection. Okay, so we need a point on the line of intersection. And last time I said just try setting z equal to 0. So we'll do that again. You can alternatively set x equal to 0 or y equals to 0. Now, this will fail, okay, if the line of intersection doesn't cross the xy plane, which is totally possible. So then you're like, well, how would I know? Because you run into an issue. So if it fails, then afterwards you can try something else. You can try x equals 0 or y equals 0. And don't worry, at that point, like something will work. I won't give you something so demented that you can't find a point on the line of intersection easily. Okay, so if I set z equal to 0, then I'm going to have x plus y equals 1. And then x plus 2y equals 1. And let's see, if I take the top equation and I'm going to subtract it from the bottom one, x cancels out and I just get y equals 0. And if y is 0, then x is 1. So the point 1, 0, 0 is on the line of intersection. You know, you probably could have just guessed that. Like, look, in your head, if you just go 0, 0, 0, 0, boom, x is 1. Some people are better at spotting stuff like that. But if you're not, just go through this process. Okay, so yay, 1, 0, 0 is on the line of intersection. Now, to write the equation for this line, I need its direction vector. Well, let's think about something. This direction vector of the line is perpendicular to both planes. Normal vectors. Because like I showed in the picture earlier, the line of intersection belongs to each of the planes. It's in each of the planes. So therefore, since it's on the plane number 1, it's perpendicular to that normal vector for the first plane, and it's also in plane number 2, so it's normal, or it's perpendicular to the normal vector of the second plane. So it's mutually orthogonal to both their normal vectors. So all I need to do is take the cross product of their normal vectors, and I will have the direction vector for our line. So 1, 1, 1 is the normal vector for the first plane. 1, 2, 2 is normal vector to the second plane. So here I will get my direction vector. If I cross those two guys, what do we have? 0, 1 minus 2, -1, and then 2 minus 1, 1. So direction vector for our line has components 0, -1, 1. And the problem asked us to find the parametric equations for the line of intersection. So I'm going to write x equals 0t plus 1, so just x equals 1. Y equals negative 1t plus 0, and z equals 1t plus 0. So here's the parametric equations. Now remember, the equation of a line in 3 space is not unique. So you could have had a different point on the line of intersection. Your equation would look a little different, your parametric equations, but the direction vector should still be a scalar multiple of 0, negative 1, 1. Got it? Okay, and then to find the angle between the planes, again, I'm going to find the angle between their normal vectors. So for part B, the angle between the planes is the angle, we'll call it theta, between their normal vectors. Maybe I should call them something. We'll call this one n1 and this is n2. So cosine theta, here it is, our most useful formula, equals n1 dotted with n2 over magnitude n1, magnitude n2. So let's see, their dot product's going to be 1 plus 2 plus 2 over square root of 3 times square root of 1 plus 4, that's 9 again. So this is 5 over 3 rad 3. And then theta is going to be cosine inverse of 5 over 3 rad 3. Did they say how many decimal places to round to? I'll just round to 1. I forgot to do this part earlier when I was prepping everything. Please forgive me. 5 divided by rad 3 rad 3. Okay. Ooh, 15.8 degrees. Okay. That's done. Let's move on. Find an equation for the plane consisting of all points that are equidistant from the points 1, 0, negative 2, and 3, 4, 0. Call this point A, call this point B. Here they are in space. We want the equation of the plane that contains all points that are equidistant from these 2 points. Well, let's think about what's going on here. Connect these 2 points. The midpoint is obviously going to be on this plane. It's equidistant from those 2 points. A point over here, a point over here, a point over here, here, here. These are all going to be on the plane because they're equidistant from A and B. And then I can also project this outward, or actually towards us kind of, but it's hard for me to show the perspective, and this becomes a plane. Let's get rid of this mess. So you can see how it's going to be a plane because I have infinitely many points up and down in this direction, and then I can go towards you and into the screen. Okay, so if we're trying to find the equation of a plane, remember we need 2 things. We need a point on the plane, and we need a vector normal to our plane. Well, right here, if I get the midpoint between A and B, that's definitely on our plane. So what's the midpoint? Just average the coordinates. 3 plus 1 divided by 2 is 2. 0 plus 4 divided by 2 is 2. And then negative 1. Now I need a vector normal to our plane. Well, if you just make a vector connecting A and B, that's most certainly normal to our plane. So the vector AB is normal to our plane. And AB would have components 2, 4, 2. Well, how about instead we divide everybody by 2 and we use 1, 2, 1. Okay, and that's it. There's our normal. We've got a point, so 1 times x minus 2 plus 2 times y minus 2 plus 1 times z plus 1 is 0. And then we have x plus 2y plus z is equal to, this is -2 and -4, so -6 plus 1, -5, and then I'm going to move it over and it's +5. All right, good job. And moving on now, as I said before in the first video lecture and in class, you're not allowed to use any memorized formulas for the distance from a point to a plane or other garbaggio like that. You need to show that you understand the concept and the setup. And if you look at the solutions manual for some of these exercises, because they are so reliant on that formula, distance from a point to a plane, they make other problems a lot more convoluted than they need to be because they don't conceptually set it up. So please don't look at the solutions manual and take it as, you know, like the Bible of math, and it's not well done always, okay? Sometimes it's helpful, but in this particular case, follow the process that I'm outlining here so you understand the concept. Okay, find the distance from 1, -2, 4 to the plane that's given here. So I'm going to draw you a picture, and I recommend you do the same thing. So here's our plane. There's some point here, let's call it P, in space. And we want to know what the distance is from that point to our plane. Well, when we say distance, of course, we mean the shortest distance, right? So if you were to drop a perpendicular, and how can we find that? So what we're going to do first is connect that point to our plane. So we're going to find some other point on our plane and connect it. Okay, we're going to call this point Q or whatever. So connect the point to our plane. Then what I need to do is take that vector, QP or whatever, and find its scalar projection along the normal vector to our plane. So connect the point to our plane, then find its scalar projection along n. Then that will give me the distance that P is from the plane, because I'm taking this vector, its scalar projection is a scalar, so it will just be the distance in the direction of the normal vector. It will give me this quantity here. So first let's find Q. We need a point on the plane. So just do whatever you want. I'm looking, this is a 5. Like, I don't want fractions in my life, okay, if I can avoid it. This is a 5, and I know 3 plus 2 is 5. So how about x is 1, y is 1, and then z would be 0. I was just trying to do something nice. 1, 1, 0. Perfect. That's on our plane. By looking, by inspection. So now let's make a vector from Q to P. So the components would be 1, -3, no, excuse me, 0, 0, -3, and 4. Okay, that connects the point to our plane. So the distance, now I don't know which vector might be longer, so let me just take the absolute value of the scalar projection just to make sure it's not negative. The distance is going to be absolute value of scalar projection of that vector QP along n. Okay, so what's n? We didn't write it out yet. N has components 3, 2, 6. Perfect. So here we go. This is going to be absolute value of n dotted with QP divided by magnitude of n. N dotted with QP, I can already tell it's not going to be negative, so I don't need to keep absolute value. It's going to be 0 minus 6 plus 24 divided by magnitude of n, which is square root of 9 plus 4 plus 36. Good? Okay, so -6 plus 24, that's going to give me 18 over square root of, 49. How nice. So then we could say the distance is equal to 18/7. Beautiful. How are we doing? Good? Okay, so this is how we find the distance from a point to a plane. Next setup. Okay, number 18. Find the distance between the given parallel planes 2x minus 3y plus z equals 4 and 4x minus 6y plus 2 equals 3. Now I can tell that the planes are parallel because at first glance their normal vectors are scalar multiples. Hopefully you can see that. So n1 has components 2, negative 3, 1. n2 has components 4, negative 6, 2. So yeah, those are scalar multiples, so I know these planes are parallel. So let me just draw a little scenario. I have that ready to go. I want the distance between the two planes. So obviously we mean shortest distance, distance that is perpendicular to both. Okay, this is the distance perpendicular to this plane and the one up above. So how am I going to do that? Well, you're going to first find a point on each of the planes. So I don't know, say you pick a point here, and if you're just guessing another point on the other plane, you're not going to guess the one that's exactly perpendicular to both. So say you pick a point over here. Okay, we're going to connect those 2 points and make a vector. Then, in order to find the distance, I need to take this vector and find its scalar projection in the direction of the normal vector to either plane. They're the same, right? Because they're parallel. So you can find the scalar projection of this vector along n1 or n2. It will be orthogonal to both planes. I would say let's just find the scalar projection along the more reduced version. It'll just make life easier. So we need to connect the planes. Making vector p1, p2, and then the distance is going to be, always take absolute value just in case that scalar projection comes out negative, and we'll find the scalar projection of p1, p2 along n1. You could also project it along n2, no problem. You'll just be dealing with bigger numbers. Okay, so how do we find a point on each plane? Just plug in stuff for the first 2 variables and see what the third one's going to have to be. So if this is 1 and y is 1, then that's negative 1, z would be 5. So I'm going to call p1 1, 1, 5. And then p2, you could just say, hey, 0, 0, and then z would be 3/2. You have infinitely many choices, so just have at it. And then now I'm going to make that vector p1, p2 connecting the 2 planes. So we'll have for the components of p1, p2 negative 1, and then 3/2 minus 10/2 is negative 7/2. Okay, very good. So now all I need to do, this vector is connecting my 2 planes. To get this distance here, I'm going to find this scalar projection along, let's do n1. So the distance is going to be absolute value, scalar projection of p1, p2 along n1. So this is going to be absolute value of dot product of p1, p2 and n1 divided by magnitude of n1, which is square root of 4 plus 9 plus 1. So let's see. This dot product's going to give me, in the numerator, negative 2 plus 3 minus 7/2 over the square root of 14, yes? So that's going to be, this is negative or positive 1, so 2/2 minus 7/2 is negative 5/2. Taking the absolute value is 5/2 over rad 14. So then I would just write for the final answer, this is 5 over 2 rad 14. Boom. There's our distance. Okay. Very good. Now the last one I'm going to do, I didn't assign in the homework, but it's an important problem. and it comes up a lot, so I figured why not show it here. So let L1 be the line that goes through the origin and the point 2, 0, negative 1, and let L2 be the line that goes through the points 1, negative 1, 1, and 4, 1, 3. Find the distance between L1 and L2. Ooh, okay. So L1 goes through 0, 0, 0, and 2, 0, negative 1. Let's find the direction vector for that line. It would have components 2, 0, negative 1. And then L2 goes through 1, negative 1, 1, and 4, 1, 3. Its direction vector has components 3, 2, 2. So I can tell the lines are not parallel. Their direction vectors are not scalar multiples of one another. So if I want to find the distance between them, they're in different planes. These are going to be skew lines. They don't intersect. I'm just going to draw something that's, I mean, it looks like it's in 2 space, but just hopefully to get you understanding the concept of the setup. Okay, so I want the distance between these 2 lines. That's going to be the distance. What do we need to do? Well, very often we just connect the lines somehow. So you get a point on each line. We have that, that's no problem. And we connect them. I'll call that vector A. Connect the lines. Then, to find that distance, I need to find the scalar projection of A, and that scalar projection has to be perpendicular to line 1 and perpendicular to line 2. I'll say it again, because this distance, right, it has to be perpendicular to both. So connect the lines, find vector A, and then the distance is the scalar projection of A along a vector that's normal to both of the lines. How can I find a vector that's normal to both of the lines? You cross their direction vectors. So find the scalar projection of A along the cross product of V1 and V2. So I'll say it again. I'm going to connect the 2 lines. We'll call it vector A. Then in order to find this distance, right, it needs to be perpendicular to both of the lines. So I have the direction vectors of each of the lines. If I take their cross product, I'll have a vector that's mutually orthogonal to both of the lines. So that new vector, I'm going to project A along it, find its scalar projection, and bam, there's my distance. Okay? So first, let's find vector A. We just need to pick a point on each line and make a vector. Let's just use these first 2 right here. So vector A has components 1, negative 1, 1. Love it. Now we need to find V1 crossed with V2. I'll call it N because it's normal to both, right? So N is V1 crossed with V2. They're already stacked here nicely, waiting for you to take their cross product. And so we get 2, negative 7, 4. Perfect, perfect. So then this distance D is going to be, let's put absolute value just to make sure it's not negative, scalar projection of A along N. So we'll take absolute value, A dotted with N, divided by magnitude of N. So A dotted with N is going to give us, let's see, 2 times 1, so that's 2. Negative 7 times negative 1, so plus 7 plus 4. Over magnitude of N, which is square root of 4 plus 49 plus 16. Very good. So in the numerator, we've got 2 plus 7 plus 4. So that's going to be 13 over square root 49 plus 20 is 69. And there's our distance. So that concludes the video. What a triumph. If you made it to the end, let me know in the comments down below. But hopefully after this, you feel a lot more comfortable setting them up on your own. Definitely, it just takes a lot of practice, repetition. And since the setup of each one is always slightly different, it's easy to get overwhelmed. So just remind yourself, what do I need? What do I know? What have I done successfully? How can I get to that same scenario? I was trying to talk you through my thought process this entire video. And seriously, get in a study group and practice explaining these problems to one another. That'll help tremendously. So don't forget to give the video a thumbs up, subscribe if you haven't already, and if you need help with any other topics in Calc 3 or Calc 1 and 2, then check out the playlist on my YouTube channel. Love you all. Thank you so much for your support, and I'll be back sooner than later. Bye.